And welcome back, everyone. I'll go ahead and share my screen again. And so that's nice to have a little break when we have like a 2-hour session. But then what we're going to next is now looking at power transmission. We kind of indicated earlier on that torque often occurs in power transmission situations. And so we can look at that power aspect. Power is just going to be equal to the torque times really that derivative of radial position with respect to time, or your angular velocity omega, which is d theta dt. So your power is equal to torque times omega. And so this is helpful because if you know, say if you have an electric motor and you know how much power it consumes in watts, for example, and you know the rotational speed of the shaft, you can calculate the amount of torque that's being transmitted through that shaft. And so again, power is going to be in watts or horsepowers, and 1 horsepower is 550 foot-pounds per second. Torque is going to be in something like Newton meters or pound-foot. If you're in the SI or the English system, theta is your angular rotation in radians. Omega is your angular velocity in radians per second. And then you can look at the power transmitted by a rotating shaft. But oftentimes torque is often not constant. Think about your engine, for example. When you're going at a low speed, you have a lot of torque, but as you speed up, that torque drops off, so that manual engine, manual transmission, you have to shift that into a higher gear to increase your torque again. And so then what about work? Again, if you want to know the work being done and not the power, if you plot the torque versus the angular rotation in radians, that area under the curve would be equal to the torque throughout the change in the angular twist. This actually worked out very well for a catapult analysis that we did back in what is now like GES 130, like just an introduction to engineering course. But we had projects for the first year students at that time, and the project that year was making catapults, and we used a twisted rope bundle essentially to place the catapult arm between the twisted rope bundle, and then twisted the rope up. And when you do that, you develop a lot of torque in the rope. You pin that in so it's not able to unwind, but then you kind of have a preload on the beam so that when you pull that back, you're causing that rope to twist even further and develop more torque. And then when you release it, that all gets released, say from that high point on the graph down to the low point, say where it hits the stop member, and launches the object. But there were some interesting issues that were coming out based on what students were doing, and what they were seeing in terms of the ranges they were able to throw. Some teams were making longer throwing arms and throwing a lot longer distance. And the math that was provided within the chapter didn't really explain that too well. And so one of the retired faculty stopped by to see me, and they're like, can you help explain all these different changes students are doing and what impact that has on the throwing distance? I was like, well, sure, this is dynamics type stuff. So this is one of the first things that I did with some of the students was measure this torque versus angular position We could do that just with a force meter and looking at that torque at every given or at different intervals. And this was a nice, I think it was a nice power curve relationship that we had. And so we could calculate the amount of work that was going into moving the arm up. But that was a function of both the rotational motion of that arm, how much energy it took to get that moving, plus the energy of the payload. Some of the things that were being noticed again was the longer arm, longer distances. Also, a lot of the arms were being broken when it hit the cross member. And through that dynamic analysis, I kind of found that about 30% of the energy was going into actual energy to launch the projectile. We were using a tennis ball, and about 60%, a little bit more, was going into just stopping the arm from moving. So that's why a lot of the cross members were breaking. And so that kind of helped explain that to the faculty member. And then we kind of, as a group, shared that with our individual sections so that they could do their analysis properly. And that year I volunteered. They wanted the competition not to be of a distance, who can throw the farthest distance. They wanted to see which team could hit a target. And so that year I volunteered to be the target. I stood back about 70 feet and kind of crouched down. I didn't want to be like super tall. I'm like, I got to make it a little difficult for you. But I had about 10 teams, and there was only 2 teams that hit me. But we kind of put chalk on the ball too so that we could identify where it landed. And so we could see how close all the teams got. And then the one team, it was a nice gentle arc that just kind of bounced off my head. And that was fine. The other team that hit me, it was kind of a straight line shot. They kind of angled their catapult, and I just kind of turned my head away from them, and I took the shot. And I'm glad we were using tennis balls, but I think the first year students like that opportunity to peg me with tennis balls for that project. And it's a tennis ball, so it's fine. And so if we look at an example problem with power involved, say we have a 3-meter long hollow shaft, shear modulus of 80 gigapascals, outer diameter of 100 millimeters, inner diameter of 60 millimeters, and a maximum shear stress that we don't want to exceed of 80 megapascals. That's our limit. And the shaft is spinning at 200 revolutions per minute. That's a common thing with angular velocity, even though we want to know that in like radians per second. Shaft speeds are often defined in revolutions per minute. And so we want to find the power transmitted and then that angle of twist throughout that 3-meter long shaft. And so to do that, we're given a stipulation on the maximum shear stress. So with that, we could calculate what the maximum torque is that we could transmit, and then torque times our angular velocity. When we do the unit conversion, will give us our power transmitted. And so we can start out with the maximum shear stress is equal to TC over J. Again, C is just the outer diameter over 2. J is pi over 32 times diameter outer to the 4th minus diameter inner to the 4th. And so plugging that all in, 80 megapascals, 32 times torque, diameter outer over 2 is 50 millimeters. Outer diameter is 100 millimeters. Divided by pi, divided by 100 millimeters to the 4th minus 60 millimeters to the 4th will give us then one equation, one unknown, where we can solve for torque. And I did this with respect to Newton and millimeters, so that would come out as 1.367 times 10 to the 7th Newton millimeters. And then if you divide through by 1,000, you would get 13,700 Newton meters. So we'll use both of those as we move forward. First one, we want to know the power, and so I use the 13,700 Newton meters, 2 times 200 revolutions per minute for the rotational speed. And remember again, in 1 minute there's 60 seconds, and in 2 pi radians there's 1 revolution. And so that'll give us our power output in watts. It would be a Newton meter per second. Revolutions cancel, minutes cancel, and radians is essentially unitless once it all gets multiplied through together. So it'd be a Newton meter, a joule per second is a watt. So 286,350 watts. Divide that by 1,000 and you have 286 kilowatts. When I calculate the angle twist, I'm going to use the Newton millimeter one so that our angles will come out properly. But then that's times the length, 3,000 millimeters, J pi over 32. So 32 got placed on top. 100 millimeters to the 4th minus 60 millimeters to the 4th, and G 80,000 megapascals. And that's a Newton per millimeter squared. And so we have millimeters to the 4th down here, millimeters squared here times another millimeter squared will give us millimeters to the 4th on the top and bottom. So those will cancel, the newtons will cancel, and we'll be left without any units, which will define our angle then in radians, 0.06 radians. So that's just a basic problem involving power transmission. And then next, we'll get into then the statically indeterminate cases. And so we'll just do that by example. Where we're given 2 3-inch diameter shafts. The first one is a solid circular steel, shear modulus 11,600 KSI, and bronze, shear modulus 6,500 KSI. They're rigidly connected at point C, and then they're fixed on either end. Torque T is applied at the rigid connection, and the thing that makes this problem complicated is that we're given a maximum shear stress in the steel of 18 KSI and a maximum shear stress in the bronze of 6 KSI. And what we want to do is find then the maximum torque, tau or T max, that can be applied to that assembly at that connection between the two. And so when you apply a torque, both of these are going to rotate around clockwise from that point in relation to the torque. But again, compatibility comes into play. Since they're rigidly connected, they have to rotate with that same angle of twist at that point C. Otherwise, they would be rotating in relation with one another, and they're rigidly fixed there. And so we have to make use of compatibility to determine what those internal torques are, and to be able to solve that. Because if you were to draw a free body diagram, if you cut both sides, you would have one torque applied and then the unknown torque in the steel and the bronze. So we have essentially one equation and 2 unknowns, just like we saw with statically indeterminate for axial loading. What makes this problem difficult is that the torque is not given. If the torque was given, this is a little bit more straightforward a problem, because we can just calculate out what the shear stress is and the angle of twist is when we make use of compatibility but we're given a constraint on the maximum shear stress. So we need to find what the maximum torque is the steel can be subjected to, the maximum torque the bronze can be subjected to, and then relate that all together. And so we'll take you through that process. And there are really two methods to do that. Your intuition really helps out again in this one with respect to signs. If we assume what's happening, then we really can avoid having to keep track of signs in that process. And so if we look at this intuitively, we'll have a reaction torque going around in the X direction, a positive torque, counteracting this torque that's applied. And same thing, you would have that torque acting in the counterclockwise direction to counter this torque that's being applied. And so if we draw the free body diagram in that manner, where both of those torques at A and B are opposing the torque that's applied, we're going to be able to neglect the signs associated with that in our analysis, and just look at those in terms of magnitudes. And so if we sum moments in the X, we'd have really a TA plus TB minus a torque is equal to 0. And if we looked at that on a torque versus position diagram, that would be a negative TA and a positive TB. But again, we're neglecting the signs in that. And so our compatibility relationship then, neglecting the signs, is we're just saying that angle of twist for that first segment, AC, is going to be equal to the angle of twist for that second segment, BC. And we'll take a look at that again. Again, we'd have section AC and section BC, the left and right half. And so that's our compatibility relationship to constrain the fact that the twist at C has to be the same at that point for both sides for the material to be rigidly connected. And then we can place in the relationship then for that angle of twist, torque at A, LAC over JAC, GAC. And that's going to be equal to the torque at B, LBC over JBC divided by GBC. One benefit that we have for this particular problem that may not always be the case is that the diameter of each rods are the same. And so JAC is going to be equal to JBC. And if that's the case, you can just cancel them out and not have to worry about them in your analysis. But you can only do so if they are the same values. But then we can rearrange this to solve for TA as a function of TB and plug our values in there. We have 8 feet for LBC, 5 feet for LAC, GAC 11,600 KSI, GBC 6,500 KSI. We really don't need to convert these to inches at all because their units cancel. 8 divided by 5 is going to give you the same value as if you converted this to inches and divided the two together. So all these just work out into a numerical scaling between TA and TB. So TA is equal to 2.855 TB. And then if we plug that into equation 1, looking at our summation of moments about X, now we can take a look at that further again too, just recalling if we have our positive X direction, thumb going in that direction, we'd have a TA plus TB minus T is equal to 0. And so all we're doing now is substituting TA of 2.855 TB into that first term. And so 2.855 TB plus the other TB minus T is equal to 0, which tells you that the torque is equal to 3.855 times TB. Again, these are just relating the two torques together, We don't know what the torque is that's applied, and we don't know what the reaction torque TB is. So we're still one equation, two unknowns. And so that gets us to the point of what they did provide for us, and the given was the maximum shear stress that was allowed. And so we want to know what is the maximum TA and TB based on those shear stress limits. And so we can calculate the torque, the shear stress for AC is equal to torque at AC over J. J is just pi d to the 4th over 32, or C is equal to D over 2. When you do that for a solid circular shaft, what you'll find is that we have TA times a diameter over 2 for the C value, and a pi d to the 4th over 32 for the J value. And 32 divided by 2 will give you 16. TA over pi, and then a d will cancel with the d 4th to give you d cubed. So make a note of that for a solid circular section. Tau max is equal to 16t over pi d cubed. That's a handy bit of knowledge if you're dealing with solid circular shafts, relating that in terms of the diameter. And so for the one material, the yield strength is 18 KSI. And so that gives us a maximum torque of 95.426 kip inches. And if we do the same thing for section BC, we find its maximum torque is 31.809 kip inches. And then at that point, we can speculate if the bronze yields first, if we put 5 into 3 above. TB is for the bronze material. We just find that that torque would then be, if the bronze yields first, the torque applied would be 122.6 kip inch. And then if the steel yields first, TB is equal to TA over 2.85. And so if we plug that in, TA over 2.855, and put our yield of 95.426 kip inch for TA, we'll find that the torque that the steel will yield is 128.9 kip inch. And so we want neither of the materials to yield. And so that tells us the maximum torque that can be applied is this lower one, the 122.6 kip inch. What that means is that the shear stress at A is going to be slightly lower than this, because we're not ratcheting it up all the way to the 128.9 kip inch. So we find that 122.6 kip inch is that maximum torque value that can be applied. And I summarize that there. It takes a torque of 128.9 kip inch for the steel yield and 122.6 kip inch for the bronze to yield. So that tells you the bronze will yield first, and that tau max is equal to 122.6 kip inch. Then based on that, we can substitute that back in to find that TA is equal to 90.8 kip inch and TB is equal to 31.8 kip inch. And so the torque in the steel, 90.8, is just slightly lower than the maximum that it can also withstand. The other thing we can look at in terms of our equilibrium expression that we first had up here, just to verify things are correct, we had TA plus TB minus T is equal to 0. And so we can satisfy equilibrium. If we add these two together, 90.8 plus 31.8, that would be 16.2. Since we carried the 1, 9 plus 3 is 12, would give us 122.6 kip inch. And so we are doing a verification check just to make sure we are good with equilibrium based on the numbers that we calculated here. So those numbers do satisfy equilibrium. And then we want to know what is the angle of twist at C. And again, we can use either expression. We can look at the bronze section or the brass section and calculate the angle of twist TB times LBC over JBC times GBC. And so 30, this is again pi d to the 4th over 32 times the torque times the length, an 8-foot shaft times 12 inches per foot divided by the shear modulus will give us an angle of twist of 0.059 radians. And as a solution check, do the other segment of steel and calculate its angle of twist, TA, LAC, GA over GAC, GAC. And you'll find that you have the same angle of twist. And so again, with these compatibility type problems, it's definitely helpful to do that verification and check both of them. If they equal one another, it's a good day. You know you've done your math okay. The second method is a little more complicated because you have to draw the correct free body diagram and then retain your signs throughout. So the correct free body diagram, again, using your right hand rule, coming out from the cut, a positive torque would be counterclockwise. Our torque is applied there, and T of A, the thumb facing away from the cut, would place a positive TA going around in the clockwise direction, same as T. And so your equilibrium expression, the sign on T of A changes. And then when you look at then the equilibrium expression, instead of just setting the magnitudes equal to one another, if we look at the angle of twist of C relative to A, if we make a cut here, that's going to twist back, but that's going to be a negative. If we were to look at this left-hand segment, a positive twist would be counterclockwise, and a negative twist would be clockwise in the direction of T. But if we look at the second segment, steel, and then bring our thumb out, the positive twist is in the direction of the torque. And so I think that's where it gets most confusing, is keeping track of what happens if you make a cut there. Since one side would be negative, the other side would be positive. For those essentially to be the same and how they're twisting in the direction, that forces that compatibility statement to be a sum. Again, they're equal and opposite due to Newton's third law and just our positive definitions. And so that'll cause that to equal to 0. As we plug all that information in, then we can calculate TA as a function of TB. We end up with signs throughout that. And so the main thing is it's those initial parts where the signs are different. And then the rest of the solution process is the same, but the torque at B will come out as a positive value and torque at A will come out as negative to show that it's acting in the opposite direction. And likewise, the angle of twist for CA will be negative. The angle of twist of CB will be positive. But the main thing again too is that this problem would have been a lot easier if that torque would have been given, but that's not always the case. So you have to be able to tackle these however that problem statement is set up. Oh, let's see. I think we're doing good on time. This one should only take 20 minutes, so we'll be good on getting this done. That last problem that was statically indeterminate was about the only one you can do where you're just setting the angle of twist, the magnitudes equal to one another. Of the two methods that we just talked about, I kind of prefer the intuitive method. I did that as an undergraduate just because I didn't have to deal with signs at that point. But then when you get any more than one torque applied to your shaft, or if you have multiple sections with different materials or different diameters, that intuitive method kind of falls apart. You're not really able to set things equal to one another at that point. And so you really need to make use of the principle of superposition at that point. That's where this really comes into play, that's able to solve these easily. And so looking at this example problem, say we're given a 60 millimeter diameter shaft, a 99.2 steel, and it's fixed at both ends, A and B. And then there's two torques applied, TC and TB, of 500 Newton meters and 200 Newton meters respectively. What we want to do is find the absolute tau max in the shaft. And so same thing, we're kind of stuck. If we were to draw a free body diagram, we would have one equation and two unknowns, the torque at A and the torque at B. And so we're stuck from an equilibrium standpoint. We don't have enough equations to solve for the number of unknowns, TA and TB. And so we need to make use of compatibility to solve for that. And it actually works out fairly straightforward. But with superposition, what we can do is replace our fixed support A with a corresponding torque at A. And one thing we can kind of use intuition in this process, or we can just stick with positive definitions. If we were to use intuition, we would know the torque at A and the torque at B both act in the opposite direction as C and D. But we could draw that in a positive sense for both of those, since we kind of did that the other way on the last problem. So T of A would be down in that direction. TB, that cut would be causing that to come around in the other direction. So for this one, we'll not assume directions and just let the math do itself. And so for the principle of superposition then, what we're really doing is just looking at that as a fixed boundary at T sub B, and then looking at each one of these loads separately. We'd have the torque at A applied. That would act over the entire length of the shaft. We'd have torque of C applied. That would act over the approximately 2/3 of the shaft, everything towards the fixed end. This is free at this point to the left, so it's not going to cause any changes to that section. And TD would cause a twist for that final third of shaft nearest the base. And I'm sure the values for those lengths are not quite thirds, but again, the torque at A would be for that full 3.5 meters of length. The torque at C would be for 2.5 meters of length, and the torque at D would be for that remaining 1 meter of length. And so from a compatibility standpoint, we know that the twist at A is equal to 0, since that's a fixed support. It can't twist at all. And so that's going to be really the twist due to the torque at A minus the twist due to the torque at C minus the twist due to the torque at D. And so this is now our compatibility statement to force the far left side to have 0 rotation. We can call that equation 1. And now this again is based off all the external torques, which is nice. And so we can plug in our values TA, LAB, JAB, GAB, minus TC, LCB over JCB, GCB, minus TB, LDB over JDB, GDB. And again, this problem is a little bit easier to solve than most because the diameters of the shafts are the same, the materials are the same. And so we can multiply left and right side by those values since those are all equal to one another. 0 times those values are still 0. So we're just left with what's in the numerator. And we can solve for TA as a function of TC and TB. This one was a little bit kinder because they gave us those torque values. And so we can calculate then the reaction torque at A is 414.3 Newton meters. When we plug that into a summation of moments, we can find that TB is equal to a minus 285.7 Newton meters. And if we were to draw the torque on that, it's going to be 414.3 Newton meters. It's going to step down the 500 Newton meters, I believe. I'd have to look back. Oh, I went way back. Not that far back. Right, so 500 Newton meters. So yeah, we start out at 414.3 Newton meters. We drop down 500 Newton meters to minus 85.7. We drop down another 200 Newton meters to minus 285.7, and then that reaction force brings us back. But what we see in this situation too is that, we won't go back so far this time, the torques that are applied are 500 Newton meters and 200 Newton meters. But even though a 500 Newton meter torque is applied, the largest torque that the shaft actually experiences internally is 414.3 Newton meters. And so that's our maximum shear stress. And again, what we're solving for is just the absolute maximum shear stress in the shaft. And this is our maximum torque. So now we know our maximum torque, 414.3 Newton meters. And so we can calculate the maximum shear stress from that. And again, solid circular shaft, that's 16T over pi d cubed. That's fine to use that if you're dealing with a solid circular shaft. You don't need to derive that each time. And so we have 16 times 414,300 Newton millimeters divided by pi divided by 60 millimeters cubed will give us 9.77 megapascals as the maximum shear stress. And that does it for that problem. But again, just solving those internal torques takes a little bit of effort with the method of superposition to be able to do that. There are some problems that you'll run into where instead of saying that the boundary is completely fixed, they'll say that it's restrained. And with that, they then allow a certain amount of rotation, say like 0.005 radians, before it comes to a stop. And so it has a little bit of compliance to rotate. In those situations, if say it allows 0.005 of twist, this value would no longer be 0, it would be that 0.005 radians. And you'll see what happens if that's 0.005 on this side. You couldn't directly just cancel out your J and G values. That would have to be multiplied through by that 0.005 on the left-hand side. So there would be a finite value on that when you're finding that relationship for TA. Likewise, if these values aren't all equal to one another, you'd have to retain that in solving for T of A. It wouldn't be a strict relationship between the torques that are applied and the lengths. The J and G values would show up in that too. If those values are given, I would probably recommend just plugging your values in and finding the quantity in front of TA. So work these out into numbers, and then it's easier to get that relationship, and instead of doing the algebra with letters there first. But you can do the algebra with letters first if you want. And so with that, that gives your maximum shear stress. And so are there any questions at all?
Yeah, I have one.
Yep.
So on that last example where the applied torque is 500 Newton meters, but then the internal torque is less, I guess what's happening to the rest of that torque that's being applied? Is it being absorbed by the rigid connections?
Right. And so the torques that are applied along with the lengths of the shafts are dictating what the boundary reactions are. And so the torque at A is in this opposite direction. And so that would be the torque that's subjected within this first portion of the shaft. And then since TC is 500 Newton meters in the opposite direction, it's relieving that torque at A and dropping that down to a negative value. TD is dropping that down to a further negative value, and then TB acts in the opposite direction, so it's bringing that back up to 0. And so it's similar to the previous problem where it really requires your free body diagram to figure out what those internal torques are. Does that answer your question,
Yeah.
Jordan?
Yeah, that makes sense.
Any other questions? All right, I'm gonna go ahead and stop sharing. And we'll go ahead and call that good for today. And then that really kind of covered all the information on torque of circular sections. On Wednesday, we'll start discussing the torque of non-circular sections. So thanks for your time today, and then we'll see you on Wednesday.